লিথোগ্রাফি, হোয়াট ইজ লিথোগ্রাফি? আমরা একটা ভিডিও দেখেছি। লিথোগ্রাফি ইজ ইজ এ টাইপ অফ প্রিন্টিং। অ্যাকচুয়ালি এই যে প্রিন্টিংটা, এই প্রিন্টিংটা ডেভেলপ হয়েছে তোমার লিথোগ্রাফি থেকে। হ্যাঁ, লিথোগ্রাফি কি হয়েছে মেইনলি ওটাতে তোমরা দেখেছো, মনে আছে কিনা জানি না, একটা স্টোন ছিল, স্টোনের উপরে তোমরা একটা ফিগার ড্র করেছো বাই এ স্পেশাল টাইপ অফ পেন। You have sketched a figure by a special type of pen. হ্যাঁ, স্পেশাল টাইপ অফ পেন মানে হচ্ছে ওই পেনটা, ওই পেনটার কালিটা দিয়ে বা ওই পেন্সিলটা দিয়ে তুমি একটা ফিগার তুমি ড্র করেছো। এখন তুমি যখন ওই ফিগারের উপরে ইঙ্ক দেবে, তুমি যখন ওই ফিগারটার উপর ইঙ্ক দেবে, ইঙ্কটা শুধুমাত্র ওই যে লাইনগুলো পেন্সিল দিয়ে ড্র হয়েছে সেই লাইনগুলো দিয়েই অ্যাবজর্ব হবে, আশেপাশে কোথাও ইঙ্কটা লাগবে না। কেন লাগবে না? তুমি কেমিক্যাল দিয়ে, বিভিন্ন রকমের কেমিক্যাল দিয়ে সেই ফিগারটাকে তুমি ট্রিট করেছো, ট্রিট করে এমন ভাবে করে ফেলেছো, যখন তুমি ইঙ্ক দেবে ওখানের মধ্যে কালি দেবে, ওই কালিটা শুধুমাত্র যে লাইনগুলো আছে সেই লাইনগুলোতে লাগবে, আর কোথাও লাগবে না। এরপরে তুমি কি করো, কাগজ দিয়ে যখন ছাপ দাও, কালিটা কি করবে, ছাপটা কাগজে চলে আসবে, কাগজে চলে আসলে তুমি কাগজে জিনিসটা পেয়ে যাবে। দ্যাট ইজ দ্য লিথোগ্রাফি। Now, in this lithography, there are different stages. There are many chemical treatments on that figure, but this is the lithography. Okay. Now, the main thing, যে জিনিসটা আমরা যে জিনিসটা আমরা আমরা পাচ্ছি, আমরা যে জিনিসটা পাচ্ছি, that is the exact replica of that figure. আমি তোমরা দেখেছো, we have drawn a figure, they have drawn a figure, একটা 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 টাক মাথা লোকের ফিগার রেখেছে, they have drawn a figure, and from the imprint we got that figure only, nothing else. সেই লোকটার ছবিটার imprint we have got in the paper, nothing else. So we call that figure is a mask. What is a mask? Now, what is a mask? Mask is the replica of something. What does it mean? Replica of something means, say for example, তোমাকে বলেছিলাম গতদিন যে একটা টিনের সে আমি if I draw something, say for example, this is made of say for example it is a tin substrate. This is a tin substrate. Then I have cutted this tin like that. Say for example, I have cutted this tin like that. So this portion is empty. You see, this is tin, this is tin, this is also tin, this is also tin, this is also tin, and this is also tin. But I have cutted some tin like this geometrical figure. I have cutted something like this geometrical figure. So this is empty. Now, if I give some ink, if I give some ink like that, আমি যদি কিছু কালি এইভাবে এখানের মধ্যে দিয়ে দেই, and আমি যদি টিনটা তুলি, আমি নিচে কি দেখতে পাবো? আমি নিচে এরকম একটা জিনিস দেখতে পাবো না? আমি নিচে এরকম একটা জিনিস দেখতে পাবো না? জিনিসটা আমার কথাটা বুঝতে পেরেছো? হোয়াট ইজ মাস্ক? আমি 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 কি করেছি? I want this type of geometrical figure. So I made a mask with this type of geometrical figure, and every time I give ink here, and I will get this type of figure every time. So I do not have to draw this. I do not have to draw this figure repeatedly. I just give ink here, and I will get this type of figure. That is the mask. This is the mask. Now it depends. It depends what figure you want to draw. Say, for example, you have cutted that tin as Kamrul. So if you place the ink here, and you will get Kamrul, written form of Kamrul. Nothing you have to do. You don't have to write it. Just brush ink on that figure, and you will get Kamrul. So this is the mask. This is the mask. Now the most popular way of masking of nanomaterial is your photolithography, or the most popular way of preparing nanomaterial or a substance with nanomaterial is known as photolithography. You have seen, say, for example, this is a 2-inch by 2-inch. This is a, say, for example, this is a 2-inch by 2-inch. Say, for example, a chip, a computer chip, and there are many your transistors, billions of transistors here. Do you know what is transistor? Transistor is, say, for example, this is diode. This is diode. What is diode? This is one N-type semiconductor, and it is P-type semiconductor. Then it will be called diode. Now there are triodes also. Say, for example, you have one N-type semiconductor, then here you will get a P-type semiconductor and another N. So this is NPN semiconductor. That is called transistor. So it may be PNP also. It may be PNP also. So this is called a transistor. And you will get a billions of transistor here, billions of transistor here, billions of transistor here. In a 2-inch by 2-inch, at least 1 billion of transistor you will get in your computer motherboard, or in the processor of your computer, or in your mobile phone motherboard. So how to make this? How to make this? A very small chip of nanometer level. Say, for example, a very small chip of, say, for example, 10 micron. 10 micron means, say, for example, 100 nanometer. Now you want to make on that silicon substrate. Say this is a very small silicon substrate. This is a very small silicon substrate with 100 nanometer width. On that silicon substrate, you have to make a NPN transistor. NPN transistor. So on that silicon substrate, a portion will be N-type doped, a portion should be P-type doped, and another portion should be N-type doped again. And you see that the middle portion is very thin. So you have to prepare this thing in a, say for example, 10 angstrom, that means 100 nanometer chip. How you'll do it? How you'll do it? So you have to prepare a mask. So you have to prepare a mask for doing it. How to prepare a mask, we'll tell you later, but you have to prepare a mask for doing it. And after preparing a mask, what will we do? I'm explaining you later. So to prepare this type of chips, or to prepare this type of integrated circuits, oh, you have to connect these small circuits, billions of circuits here. You have to connect all the circuits by metallic metallic connection, otherwise they will not work. So this is a very very high tech, your high tech thing. So how you can do? You can do it easily if you can prepare a mask. If you can prepare a mask, then you see, for example, this is a very complex. Say for example, a very complex figure, a very complex figure. You have to a very complex figure. This is a very complex figure. Now you have to repeat it. Say for example, 1,000 times. You cannot repeat it once, because it is so complex that the repetition of this is very difficult. But if you can create a mask with this, if you can create a mask like this with this figure, then you can repeat it 1,000 times, millions of times. How? If you have created a mask like this, and you brush paint here, and you will get the result. You can repeat it 1,000 times. You can repeat this figure 1,000 times. No problem. You will not have problem. If you just brush this, if you just brush this, you will get this figure. Always you will get this figure. Now, if you prepare this type of mass, then this thing you will get 1,000 times, millions times, this particular thing. But if I tell you that draw it again, it will not be possible for you. So you have to prepare a mask to get a to get this type of complex complex material repeatedly. You have to prepare that. So preparation of mask is 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 the main thing here. Preparation of mask is the main thing here. For this type, for this small type of your your for building this small type of substance, it is not difficult. Preparation of this mask is not difficult. You just cut the tin here and you'll get it. It is not difficult, but it will be difficult, and it will be more difficult. So we'll see what is photolithography. The most popular lithographic technique is photolithography. Now we'll see what is photolithography, and then we'll discuss how to prepare the mask. It is not that much hard what we are thinking, because we have computer. You just give the design to the computer, and that computer will do it for you, do the rest of all thing for you. It will prepare that mask. It is that easy. So let's see. Let's see what is photolithography. So photolithography is the process Photolithography is the process of transferring geometrical shape on a mask to the surface of silicon wafer. What does it mean? You see, again, if I give the camera here, say photolithography is the process of transferring geometrical shape. Say, for example, this is a plus type geometrical shape. So from that geometrical shape, we can transfer this geometrical shape on a wall. Say, for example, a white wall, a wall on your room. If you want to transfer this shape on the wall or a piece of paper, what you will do? You place the mask on the wall and paint with brush. Then you will get this plus type of geometric shape. So you have to have a mask, and if you paint something, paint a brush or paint something, paint by brush on that mask, you will get what? You will get the geometrical shape like this. This is called photolithography. Photolithography is the process of transferring geometric shape on a mask to the surface of a silicon wafer. I'm telling you of the surface of wall or of the surface of paper for this mask. But for to prepare an IC, integrated circuit, what you will require? You will require a silicon wafer. What do you mean by wafer? Wafer is the substrate. Say this is a substrate, this is a substrate on which you want to draw this geometrical shape. That is called wafer, silicon wafer or silicon substrate. So, uh, uh, um, so to make photolithography, we must have a wafer or we must have a substrate on which you will get a you can have a geometrical pattern by means of a mask, and it is named as photolithography because photo, that means light, light plays some roles here. For that, it is known as photolithography. So you have to have a substrate. Most commonly, it is silicon substrate. In most ICs, integrated circuits, you will have silicon substrate, and on the top of that silicon substrate, you'll place a mask and do something on that mask, and you'll get the pattern. What you will do, I'm telling you later. Now, first thing is silicon substrate. What is a silicon substrate? Silicon substrate means it is a substrate. Say, for example, this is a substrate. This is a substrate piece of silicon. This is a piece of silicon uh, uh, in its crystalline form. That means it is a silicon crystal piece. Here, the silicon atoms, there all are silicon atoms, pure silicon atoms, about 99 point, say for example, 99999% of silicon. That much purity is required because it is nanomaterial. That much purity is required. These all are silicons, but they are in crystalline state. What do you mean by crystalline state? They have crystalline structure. Silicon has crystalline structure. For example, silicon has a tetrahedral structure, and all silicons have the same tetrahedral structure in that substrate. All silicons have same tetrahedral structure. Say, for example, this is a tetrahedral structure. This is again a tetrahedral structure. This is again a tetrahedral structure. This is again a tetrahedral structure. And it is repeated all over the silicon. That is silicon substrate. There is no fault here. That's why it is 99.999%. You will not get any point defect. You will not get any dislocations. You will not get any surface defects here in that substrate, because they are of single crystal. You will get the point defects or surface defects for polycrystalline materials, but if it is single crystal, you will not get this type of faults. So how you can prepare a silicon substrate? You have to start with silicon dioxide. You have to start with silicon dioxide. You have to have some silicon dioxide, your normal sand, but not from the Cox's Bazar, because there are many irons as impurity in silicon dioxides. So you cannot even prepare glass with that Cox's Bazar sand. You have to import it from South Africa. That That pure silicon dioxide you have to import it from South Africa without iron or other impurities. You will have many impurities in your Cox's Bazar sand. So you first take silicon dioxide and react to it, allow it to react with carbon at about, say, for example, 1900 degrees centigrade. What will happen at that temperature? You will get silicon plus carbon dioxide. You'll have silicon and carbon dioxide. Now, this silicon is about 98% pure and amorphous. This silicon is about 98% pure and amorphous. But this silicon will not work for us because we require fully crystalline silicon, and its purity should be 99.9999%. So we allow this silicon, or the people allow this silicon to make a silicon gas. It is something like HSI Cl type gas. So when it is gaseous, when this silicon is gaseous, then you'll have what? One this molecule, one this molecule, one this molecule, one this molecule. No impurity in these molecules. You'll have only this gas, only this gas, only this gas, only this gas. Yes. You'll have only this gas, only this gas, only this gas, only this gas. Say, for example, you have oxygen gas. So you will get only oxygen gas there. No impurity can adhere with this gas atom. Actually, what happens in silicon dioxide sand? Some iron molecule adheres on the silicon dioxide, and we cannot separate it. So this is impure. Now, gaseous substance is pure because nothing can adhere with that molecule. Nothing can adhere with that molecule. And this gas, we collect this gas by means of some fractional distillation, by means of some fractional distillation. By means of fractional distillation, and we have collected this. We collect this this gas. Now, after collection of this gas, we have to crack this molecule by heating. When we heat this molecule at about, say, 1500 degrees centigrade, then we will get silicon. Then we will get silicon and, say, for example, HCl, which will be removed. We'll get silicon. Now, this silicon is not yet crystalline. We have to place some seed of crystalline silicon. Just like your sugar industry, you have to place some sugar seed to crystalline the sugars. So you have to place some silicon seed here, and the silicons will adhere it to form a crystalline silicon rod type substance. This is this type of substance. Now, you take the rod and cut this rod in different shapes, whatever you want. Cut this rod and you take a silicon wafer. Take a silicon wafer, which is this is a silicon wafer, and polish it, because when you cut this, some molecules or some atoms of silicon will be displaced from the surface, which will cause surface defect. So when you polish that silicon wafer, you will get a perfectly crystalline silicon wafer. This is the procedure of making a silicon wafer. Now, it has a band gap of about 1.8 electron volt. Say, for example, a silicon wafer has a band gap of 1.8 electron volt, and the range of your physical visible light is 1.8 electron volt to 3 point something, 3.1 or 3.2, no?
3.2, sir.
3.2. Can you tell me what will be the color of that silicon wafer? If light falls on it, on that silicon wafer, what will be the color?
Sir, black.
Yes, it will be black, because it will absorb all the wavelengths. So it will be black. So all silicon wafers are black. Pure silicon wafers, all pure silicon wafers are black. So this is a silicon wafer, and we call it a substrate. Okay. Now in the first step, you see here, first step is of photolithography. How you can do the photolithography? In the first step, you take a wafer of silicon wafer, and the wafers are chemically cleaned to remove organic, ionic, and metallic impurities. Whatever impurities in the surface of the silicon wafer, you have to clean it first. So, say for example, this is one here. This is a silicon wafer. Now, second step is a barrier layer formation. A layer of a film of silicon dioxide, which served as a barrier layer. Barrier layer means a barrier between this silicon wafer and something. There will be something above this dioxide film. So there will be barrier between this silicon wafer and the things. You will find it just after some time. You will find it what will be above this oxide film. This oxide film is a barrier between two. We require it. Why we require it, I will tell you later. So what you have to do, you have to make a barrier layer of silicon dioxide above the silicon substrate. How you can do it? You can do it by reacting the surface silicon with oxygen. Then it will be a silicon dioxide film above the silicon wafer. Next one is photoresist application. What is a photoresist application? You apply some polymeric substance, some polymer on the top of your silicon dioxide film. This polymer is known as resist. You will apply some polymer. Why I am telling it? You apply some polymer upon the your silicon dioxide substrate. How you can apply that polymer? Say, for example, you see here, this is the this this round thing is a silicon wafer with a silicon dioxide thin film. Now, if you drop a polymeric drop, say for example, liquid polyethylene, say for example, liquid polyethylene. If you place a drop of liquid polyethylene here and spin this means move this, spin this, then what it will do? This polymer, they will have a polymeric layer on the top of it. If you place something, a drop of liquid here, and spin this, if you move this, what will happen? This liquid will homogeneously distribute it. So you place a drop of liquid polymer here and spin this. So this liquid will be homogeneously distributed on the silicon dioxide film. This blue thing is the resist. Now, this is known as photoresist. Here photo thing comes. Here photo thing comes. Photoresist. So why photoresist? What is their property? This is a special type of polymer, say polymethyl methyl acrylate. The polymethyl methyl acrylate is most commonly used polymer. So what your interacts, what it will do when it interacts with light? It will break down. We know the polymeric chain is long. If it interacts with light, this is its property. If this interacts with light, it breaks down to small molecules. So it is for that it is known as photoresist. There are some other polymers which are small molecules. When interacts with lights, they form a big molecule, just opposite to this, and we will have positive photoresist and we'll have negative photoresist. What is positive photoresist? The photoresist, the polymer, which when interacts with light will break down, then it is known as positive photoresist. And the negative photoresist is when it interacts with light and it forms more and more bigger molecules, then it is negative photoresist. So you see here, photoresist is applied to the surface of the wafer by high-speed centrifugal spinning. What do you know? What is centrifugal spinning? You have one centrifuge machine in your first year laboratory. That is spinning. That is spinning by like that. That is called centrifugal spinning. So you apply, say for example, polymethyl methyl acrylate on the substrate or on the substrate wafer by means of centrifugal spinning. It is known as actually spin coating. This produces a thin uniform layer of photoresist on the wafer surface. So in this process, a liquid solution of photoresist is given out from the wafer by rapid spin to produce a uniform thin layer. And these are the condition how you rotate and up to which time it will rotate. And you can use PMMA, PMGI, D and Q, all that, phenyl formaldehyde resin, all that. Now, what I told you, about the positive photoresist and negative photoresist. What is the positive photoresist? When the positive photoresist is exposed to UV light, the underlying material is to be removed. When we expose it under UV light, this, say for example, we have exposed this portion under UV light, this blue portion under UV light. What will happen? This in this portion, the polymethyl methyl acrylate polymer will break down. And if we give some solution on that, if we give, say, for example, if we give acetone on that, it will be washed away because it is broken down. The compound is broken down. You can wash this. You can wash this by using some chemicals, and it will be soluble to it will be soluble with it will be soluble with sorry it is soluble with some chemicals, with some solvent. So what will happen if you, say for example, in this region, in the blue region, if you pass some UV light, then here the polymethyl methyl acrylate will be broken down, and you can remove the polymeric substance from here by means of some solvent. That is called developer. In this resist, exposure to UV light changes chemical structure of the resist so that it becomes more soluble in the developer. The exposed resist is then washed away by developer solution. In other words, whatever shows goes. In other words, whatever shows goes. That means what? I'm telling you again, just when we read the number 5, I will tell you again. Negative photoresist. What is negative photoresist? You see here, in the negative photoresist, when you apply UV light in this portion, then it is another. It is not polymethyl methyl acrylate. It is another polymer. Say phenyl formaldehyde polymer. Say for example, this is phenyl formaldehyde polymer. If you apply UV light, then the phenyl formaldehyde polymer polymerizes on that place. It polymerizes on that place. So it is the opposite. In one case, applying of UV light breaks down the polymeric molecule, and in another case, applying of UV light polymerizes the molecule. So where applying of UV light polymerizes the molecule, it is a negative photoresist, and the other one is positive photoresist. Now, you have applied a photoresist, whatever it may be. Say it may be positive or it may be negative. You have applied photoresist on the silicon dioxide surface. Now, after applying the photoresist, you have to heat the substrate that is called pre-baking. You have applied the photoresist here. Say, for example, I applied the photoresist here, and and you hit the substrate with that polymer at about 90 to 100 for 5 minutes to 30 minutes. You heat it, uh, heat it. So this is called pre-baking. Now the question of masking is coming. You see here, this is a mask. This is a mask. It is a very simple mask. Say, for example, this is a plate here. This is a plate here, and there is another plate here. And there is a gap here. There is a gap here. Now, let us suppose here it is the positive photoresist, and you have applied UV light on it. You have applied UV light on it. What will happen? UV light will fall on that gap to the polymer solution. UV light will fall on that gap to the polymer solution, but it cannot interact with the polymeric solution that is covered by the mask. You see here, this mask covered this portion and this portion, and you are passing UV light through this way. So the uncovered portion, in the uncovered portion, the UV light falls on the polymer. In the covered portion of the mask, UV light cannot fall. So if it is positive photoresist, say for example polymethyl methyl acrylate, it is a positive photoresist. So this UV light will break down the molecules of polymer in this region, but it cannot break down the molecules of polymer here, because it cannot interact, the UV light cannot interact the molecules of polymer here. So here UV light falls on it and it breaks the molecule here. Now afterwards, when it is break here, these molecules will be soluble to in some solvent. Say for example acetone. If we treat with acetone, if we treat this thing in acetone, or if we spray acetone in here, acetone, this portion will dissolve in acetone, will be dissolved in acetone, and this portion will not dissolve. So you will get a blank space here, and this is covered with your polymethyl methyl acrylate. But if it is a negative photoresist, what will happen? The opposite thing will happen. Here UV light, what it will do when it interacts with the polymer, it will polymerize the molecule here, And in this blue portion, the molecules will not be polymerized. They are small monomers. They will be small monomers. And if we spray acetone there, what will happen? This blue portion will go out and this black portion will remain there. This is the this is the uh, mm, 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 this is the uh, function of the mask, and this is called photomask. Now, a mask or photomask is a square glass plate which is with a pattern combination of metal film on one side pattern transferred onto wafer surface. Then you place the mask on the surface of water, surface of wafer. There are three types of placement. There are three types of placement. Uh, uh, One is contact printing. That means you place the mask in contact with the substrate. That means in contact with the resist. If you do it, if you place the mask in contact with the resist, you will get very fine, very high resolution your that geometrical shape. But this will this is harmful for the mask, because the problem with contact printing is that fragments trapped between resist and the mask can damage the mask. Here, some fragments will trap between the resist and the mask, and it will damage the mask. Mask is the very important thing for us. And the proximity printing means you place the mark just some just 1 or 2 centimeter, 10 to 25 micron above. And projection printing means you place it centimeter above. So this T type of printing, if you place the mask above, the mask is safe, but you will not get the high resolution geometrical shape. But in the contrast printing, you'll get the high resolution geometrical shape, but your mask can be damaged. These are three types of your masking masking positions. Now the development. Development means you have to give some solvent to dissolve the extra polymer. Extra polymer means, say for example, can you tell me it is a negative or positive photoresist? Is it a negative or positive photoresist? You see
Negative,
here.
sir.
You see here. The positive what positive photoresist will do? Positive photoresist will break this this polymer so that it can be washed away. And the negative photoresist, what it will do, it join the polymer so that it cannot be washed away. So this is the negative, which joins the polymer, which cannot be washed away, and positive means that can be washed away. So you see, is it negative or positive? Negative means, what negative means? It will join the polymeric molecules so that it cannot be washed away. So it is here because it is not washed away. So it is a negative photoresist. You have a developer. Developer means which the solvent you use is generally tetramethyl ammonium hydroxide you use as developer. And there are two types of development. One is spin development. You give some solution of tetramethyl ammonium hydroxide and spun this. It will dissolve that polymer, or you can spray this tetramethyl. And then hard baking. Then you bake the substrate and you will get polymer here. Now, the next step is the etching. What do you mean by etching? This is here you'll get the oxide film. The yellow one is the oxide film, which we have built, which they are built to have a barrier, to get a barrier. Now, you have to etch this thing, etch the oxide film. That means you rub it and remove the oxide film. You can etch. There are two types of etching. One is chemical etching, and another one is etching is performed using by wet chemicals such as acid, or more commonly in a dry etching by exposing the material to a bombardment of ion. Two types of etching there. You can give a chemical, you can place a chemical here to remove the oxide film, or you can bombard with some ion to remove this oxide film. So what finally you get here silicon dioxide is open, and here silicon dioxide is closed, and here silicon dioxide is open here again. Now, why this pattern is required? Say, for example, you want a NPN transistor. So you can dope N here. You can dope N here. If you spray N type of molecule here, the N type of molecule doped here and here, the N type of molecule cannot be doped here. The N type of molecule cannot be doped here because the N type of molecule cannot enter to the silicon substrate because there is a barrier here, barrier of your what you call barrier of your polymer. So you can exclude some portion from the doping or from doing something by this type of your etching, or what do you call by this type of photolithographic method. And then ultimately what will you do? This thing you can dissolve with this thing with some chemical, and you'll find the silicon substrate again. So this is one kind of a small your IC circuit. You can do it by this photolithography. Say, for example, here it is blank, here it is blank, here it is blank. You have doped here, it is doped here, it is doped here, it is blank. So the main application of photolithography is IC designing process. And the other applications are in printed electronic board, nameplate, and printer plate. Also, there are other applications, but main application is in IC designing process. So you see here again the same thing. See it. This is a silicon wafer, silicon dioxide, and then this is photoresist, and this is the mask. You see, this is the mask, and if it is negative, then it will be you will get this type of. If it is positive, you will get this type, and this is the ultimate result. Any question?
Sir, the purpose of photoresist is not clear to me yet.
Purpose of photoresist. Purpose of photoresist is to prepare the is to prepare the figure, the geometrical shape. Otherwise, geometrical shape, you cannot prepare a geometrical shape. You see, if light falls through this way, if there is a photoresist, what will happen? This photoresist will be dissolved if light falls on it. And here something is dissolved. So something is opened. And in my finger region, something is closed. In my finger region, something is closed. But here something is open. So in the open place, you can add you can dope with many things. If you want to dope with boron, or if you want to dope with arsenic, you can dope it in the open place, not in the closed place where resist exists. Because if you dope with, say for example, I have come with this figure again. If I paint here, only this portion will be painted, but this portion will not be painted. Only this portion will be painted. So this is the photoresist. Full thing is photoresist. Full thing is photoresist. And from here, from this place, we have removed the photoresist. We have removed the photoresist by interacting with, say for example, by interacting with UV radiation. We have removed the photoresist, and we can dope something in this place, not in this place, because here photoresist exists. Boron will not enter into the silicon substrate, but from here and here, boron can enter into the silicon substrate by this opening. So if we do not place any photoresist here, so how can we get this this geometrical shape on the silicon substrate? If you say, for example, you have not placed any photoresist there, How can you dope in a special place? You cannot do it. Is it clear?
Yes, sir. Thank you, sir.
Do you have any questions?
Is there any basic difference between substrate and wafer?
No, not that much difference.
These are the same thing.
Both are the mainly same thing. There is some difference in substrate. You see, substrate it can be amorphous or it can be crystalline. Say, for example, we can use a glass substrate which is amorphous. We can call glass as a substrate. So substrate may be amorphous or maybe crystalline, but wafers are generally crystalline.
There is another question. You said that if we react silicon dioxide with carbon in 190 degrees Celsius, it should be silicon
1900, not 100, 1900, not 190, 1900.
1900, and then it should be 98% pure amorphous, but it should be gaseous. My question is
still no. When silicon dioxide react with carbon at 1900 degrees centigrade, it forms silicon and your carbon dioxide. Carbon dioxide will go out and you will find silicon which is amorphous and about 98% pure.
98% pure. So my question is there any gaseous impurities there? Sir, what
it
should
will
be
go
the
out.
process to remove these types of impurities?
No. What we are doing? We have a gas of say for example HSiCl, and we are collecting that gas, purely collecting only that gas by means of fractional distillation. Well, there may be some gaseous impurities, but we will not collect that impurities. We only collect that silicon containing gas by means of fractional distillation. Okay?
Okay, thank you, sir.
There may be impurities. There may be impurities. There will be impurities. Not maybe. There will be impurities, but will not collect those impurities. We only collect that silicon containing gas.
Okay, sir. I got my answer. Thank you.
Okay. Any questions? Any questions? Anybody? Okay. Our next type of this is the photolithography is the very popular process. We use it very popularly. Next one is electron beam lithography. Electron beam lithography, as the name suggests, here lithography is done by electron beam. It is done by electron beam. The substrate is coated with a thin layer of resist, which is chemically changed under exposure to the electron beam. That is, that the exposed and non-exposed areas can be dissolved in specific solvent. So in electron beam lithography, what will happen? We do not require any mask. Say for example, this is a substrate, and above it there is a resist. There is a resist above it. There is a resist. That means polymer. Now, the electron beam from an electron gun, electron beam will fall on the resist, and the electron beam will draw the pattern. This is the pattern. Fall, and the electron beam will draw the pattern by varying the electron count. This is the pattern. Now, if we develop this substrate, or if we give some solvent to the substrate, this portion will be dissolved to the substrate where electron beam attacks. Where the electron beam is exposed, this portion will be dissolved in the substrate, and this portion will not dissolve. So here you will get an opening. Here you will get an opening, and here it is closed by the resist. Now, if you spray boron here, say for example, so you will get boron is doped. Boron will be doped here, but boron will not doped here because there is the that resist is there. So this is the electron beam lithography. A very simple lithography. The basic idea, electron beam lithography is a specialized technique for creating extremely fine patterns. We can produce mask for photolithography by electron beam lithography. The mask is prepared for photolithography by this electron beam lithography. It is derived from a scanning electron microscope. The electron beams can be focused to a few nanometers in diameter, a very fine beam, the electron beam. The basic idea behind electron beam lithography is identical to the optical lithography. What is done? The substrate is coated with a thin layer of resist, which is chemically changed under the exposure to the electron beam. When electron beam attacks the substrate, attacks the resist, the portion where electron beam attacks, that will be chemically changed, which will be dissolved in a solvent. The electron beam lithography is the most powerful tool for the fabrication of feathers as small as 3 nm to 5 nanometer. A very small scale production can be possible. There are some advantages. Print complex pattern directly on the wafers, eliminate the diffraction problem, high resolution up to 20 nanometer, flexible technique. But there are some disadvantages also. I want to show you 2 videos actually of that lithography. Okay, I have one. You see that first.
Hello.
Hello.
So this is where you can draw some really nice circuits?
Yeah, this is the place. Why do you ask?
Well, I'd like to make 2 electrodes with a gap as small as possible.
Well, with electron beam lithography here, we can go to 100 nanometers, perhaps even lower.
Really? Could you do that for me?
Even better, actually. Sit down. I'll show you, and then you can do it yourself.
The construction process begins with the circuit design, which is quite straightforward through a computer interface. Here we are demonstrating the design of two interdigital electrodes. The whole circuit is 200 micrometers large, with a gap between the electrodes of 500 nanometers. The circuit is made on a silicon plate. The first step is covering the silicon wafer with a thin layer of polymer, which monomerizes when exposed to the electron beam. With the use of a spinner, a uniform thin coating of a few hundred nanometers thickness can be deposited over the silicon. The polymer is then hardened by baking it at 200 degrees centigrade. When the wafer is prepared, it is inserted into the electron microscope, where the circuit is drawn. The electron beam precisely follows the design of the circuit and only irradiates the previously defined parts of the wafer, where the electrodes will be. When we take the wafer out of the microscope, we put it into a solvent to develop it. The solvent is chosen only to dissolve and remove the parts of the polymer which were irradiated by the electron beam and leave the rest of the polymer film intact. After the wafer is cleaned, it is ready to move to the next stage, metal deposition. The wafer is placed into the sputter. This device sputters the metal over the whole surface. On the parts where the circuit was drawn and the film dissolved, the metal can stick directly to the silicon, while everywhere else there is still a polymer film between the metal and the wafer. The final step is removing all of remaining polymer together with the unwanted metal. The wafer is put into a different solvent which dissolves the polymer. The metal on the polymer also floats off, while the metal that is directly on the silicon wafer stays intact. And the result are two very small and precise electrodes.
You see, it's not that big of a deal.
Great. Then let's go and do it right away.
देखले सिलिकॉन सबस्ट्रेट देखले জিনিসটা বুঝাচ্ছ নাকি বুঝো নাই
বুঝছি স্যার